Okay, so we were interested in, given an angle swept counterclockwise from the 3 o'clock position, so I could start it. Starting there, sweeping an angle counterclockwise from the 3 o'clock position. I'm showing that in red there. So given some angle, we're interested in pinpointing the location of the bug. Okay, so we're talking about circular motion and identifying points on a circle, their location. So we were looking, so that pinpointing that location means two things, right? It means, first of all, we look at two different quantities. What was the first quantity we looked at, or we started looking at, to nail down where the bug is for any angle swept? That's right, vertical distance. So we have our horizontal diameter, and we're interested in that vertical distance above the horizontal diameter. But we said that that doesn't do the job because, like, that same vertical distance above the horizontal diameter is also, the bug also hits that over here somewhere, right? So like right about here. So there's two different places where the bug has that vertical distance. So if we want to pinpoint exactly where the bug is, we need something else. And what is that? Okay, so we're going to close all computers today. All computers are closed, and 100% of the people are going to listen, not just 75%. Okay. All right, so what's the other thing that we can do to pinpoint the location of the bug?
Distance to the left or right of the vertical diameter.
Right, so then we're going to look at the vertical diameter. And we're going to say how far to the left or right, specifically. So we define positive as for the vertical distance as above, and we define positive for the horizontal distance as to the right of the vertical diameter. So having those two quantities, so we have our, first of all, our angle quantity comes first, and then based on that angle quantity, the angle measure, we can get this vertical distance above the horizontal diameter and this vertical distance or horizontal distance to the right of the horizontal diameter, horizontal distance to the right of the vertical diameter, and those two quantities will pinpoint the location of the bug for that angle. And then if the angle changes, those two quantities change, tracking the location of the bug. Okay, so that's a recap. And where were we? We were graphing it. And so we were looking at what did we do? We said if we want to graph this and understand how, so we started with, which one do we start with? Input, measure the angle swept counterclockwise from 3 o'clock in radians. Output, vertical distance above the horizontal diameter. And how did what was our way of tracking or analyzing the covariation of these two quantities? What do we do first? We look at? Right, small, oops, I don't want that yet. Small equal changes in the input. Okay, you're making me really mad. Why is that? Axis. Okay, small equal changes in input, and then we're going to look at resulting changes in output. So specifically, we ask 3 questions. We ask, does the output, so for our small equal increases of the input, which is angle measure, and what equal increase of angle measure did we pick? Yep, so we were going to break each quadrant into 4 equal angle measures. And so the first quadrant is pi over 2. The whole quadrant is sweeping pi over 2, so if we break that up into 4, we get pi eighths. So our equal angle measure for input is pi over 8, which breaks up that first quadrant into 4 equal pieces. And so we ask 3 questions. Does the output increase or decrease? So let's look at the first quadrant. Let's review it. Does the output, the vertical distance, increase or decrease? Increase or decrease the vertical distance? Increases, right? Here, the bug is going up, right? The bug is at the horizontal diameter, and then the bug is at its highest point above the vertical diameter, so that vertical distance increased. Over here to the right, I'm showing you the changes. I'm showing you the changes in vertical distance. Do those changes increase or decrease? Decrease. So the vertical distance is increasing, but each change in vertical distance is decreasing, getting less. So what about the rate of change? The rate of change of vertical distance with respect to angle, is it increasing or decreasing in that first quadrant? Decreasing rate of change, because the rate of change just follows right from what the changes are doing. So for equal angle increments, that vertical distance changes fast at first, large changes, and then those changes get smaller, so it's changing more slowly. So it's a decreasing rate of change. And if it's a decreasing rate, then what about the graph? Concave? Down. So increasing output values, but a decreasing rate of change, which means concave down. All right, so now we're going to, for the next, you're going to work on the next part, quadrant 2. You're going to ask these 3 questions again, quadrant 2. Now we'll do quadrant 2 together, and then you guys will do 3 and 4. 3 and 4 on your own, okay? So quadrant 2. Same equal increment, pi over 8. First question we ask is, does this vertical distance, this output, does it increase or decrease? Decrease. The vertical distance is at its maximum at the top. When it goes through the second quadrant, that vertical distance goes back down to 0. So from maximum down to 0. So the vertical distance itself decreases. So we can track the changes with this same bar over here. Looking at these points can also help us in the second quadrant to look at the changes. Are the changes increasing or decreasing? The changes in vertical distance. Are they increasing or decreasing? I heard increasing and I heard decreasing. All right, so why don't you have a discussion with the person next to you. Are these changes in vertical distance increasing or decreasing? Talk. Okay. How many people say they're increasing changes? Increasing changes. How many people say decreasing changes? Oh, it's like 50-50. Okay, the changes are positive or negative? These are negative changes, first of all. Are they getting more negative or less negative? More negative. More negative. Increasing or decreasing changes? Decreasing. Decreasing. It's the same thing. We're going over and over again. Just did it on the exam. Spent a couple days before the exam. Okay, so.
Do you mind going over it again?
Yeah, sure. Okay, so the vertical distance of the bug is decreasing, which means that those changes are negative changes. Would you agree? What are those negative changes doing? Are they getting less negative or more negative? More negative. So, for instance, what did we? The radius of the fan was 2.6. So maybe I'm just going to say, let's just make up some values here. So maybe that's negative. This first change here is negative 0.3 feet. And then this next change is negative 0.7 feet. And then negative 0.9 feet. And then negative 1.1 feet. Is that close to 2.6? Anyway, it doesn't matter. So it's something close to 2.6. Okay, so that's looking at the changes in vertical distance. And since the change is going down, so negative 0.3, negative 0.7, negative 0.9, negative 1.1. So that sequence of numbers those are changes in vertical distance in feet. Is that a decreasing sequence of numbers or increasing? Decreasing. They're getting more negative. Those numbers are going down. Those numbers are going down. Now, the amount of change, just looking at the amount of change, yes, it gets bigger, and that's what's confusing about it. But because they're negative changes that get more negative are decreasing changes. Okay? So what about the rate of change in this part of the rate of change of vertical distance in the second quadrant? Increasing or decreasing? Decreasing. Therefore, the graph should be concave up or down. We've got decreasing changes in output, so we have a decreasing rate of change. So what about our graph? Concave up or down? Decreasing rate is concave down. Okay, so in the second quadrant, the output is decreasing. The changes are decreasing also, which means concave down. Decreasing and concave down. Okay, so I want you to, while I take attendance, you're going to ask these same three questions for quadrant 3. Take your time, and then once you think you got those three questions answered for quadrant 3, then quadrant 4. So get a partner, talk it out, go slow. Jerome's going to walk around and help you and make sure you're staying on task. Go slow. Don't just generalize quickly. Go through each question slowly. Okay, let's see here. Okay, Alex, you're up. Quadrant 3. Tell me about the output, the vertical distance. In quadrant 3, as we increase the angle, does the output increase or decrease? No, just the output. Increase or decrease? You want decrease? He wants the output decreases. Agree or disagree? That vertical distance is decreasing. Yeah, the bug is going down, right? The bug is going down. So from there, It's decreasing, the vertical distance decreasing. Another example, there's another example of getting more negative, right? So that vertical distance is negative and getting more negative. So it's decreasing, going down. Okay, so now what about the changes? Cody. So now the changes in vertical distance, increasing or decreasing?
Increasing.
Why? So we're looking over here. Here's our first change, and there's our next change, third change, fourth change. Increasing or decreasing?
I'm not sure.
Not sure.
I'm not sure.
Brandon, what do you think?
Can you ask me?
So we want here are the four changes in the third quadrant in vertical distance. We said the vertical distance is decreasing. That's true. That's the output. But now what about those changes? Are those changes increasing or decreasing?
They're increasing because they're getting less negative.
He said they're increasing because they're getting less negative. He's my best friend today. He said he's perfect, right? So they're getting less negative. So those changes are increasing. And if those changes are increasing, what about the rate of change? I'm sure I'm not his best friend. All right. So what about the rate of change? Changes are increasing. The rate of change is increasing. Therefore, the shape of the graph is concave up. Here we go. Going down, but the changes are increasing, getting less negative. So less negative changes means increasing changes, increasing rate of change, concave up. Okay, what about in the fourth quadrant? Down here. Christopher.
First one's increasing.
He wants that the output or the vertical distance is increasing through the fourth quadrant. They like it. Okay, changes.
Increasing.
Increasing changes. Because the changes are getting more positive. It's a bigger positive change every time. Therefore, the rate of change is increasing. So the graph is concave up. So what is this? Is tracking one full rotation of the bug's vertical distance above the horizontal diameter for one full rotation around. Okay, and so we need a unit for this vertical distance. So we could do feet. We'll do that in a second. So we know, so like if it was feet, what is the highest vertical distance in feet? 2.6, and the lowest? Negative 2.6. We'll do that in a second. But first I want to use a different unit of measure that's kind of more universal for all circles. What do we say that unit of measure that would make sense for all circles be?
Radius.
Like radius lengths, right? So radians is openness, radians is angle, but we can talk about radius lengths. What is the maximum number of radius lengths for a vertical distance? What's the maximum number of radius lengths? No, that's the angle. Vertical distance. The vertical distance. The maximum vertical distance. One. One whole radius. You can't go on a circle, you can't go any higher on a circle than one whole radius above. So everything else is really like a fraction of the radius, right? So any other place on the circle is going to be like between, what's the lowest? Negative 1. Everything else between -1 and 1 is like a fraction of a radius length. So that's going to be our unit. Since a whole radius length is the most we can get either above or below, we're going to measure our vertical distance above the horizontal diameter in fraction of radius length. That's going to be our unit, the fraction of a radius length. Okay? So what would you estimate it to be right here? Estimate the fraction of a radius length that we are above the horizontal diameter right here. Just estimate. So a third? -0.7. What were you going to say? Negative 0.9. Yeah, something like that. Something almost negative 1, right? Negative 0.7, negative 0.8, negative 0.9, something like that. That would be our fraction, and it's negative because we're below. Okay, so that's what we're going to use for our unit, fraction of a radius length. So we're measuring the vertical distance in the fraction of a radius length. Okay? So we said that that would make this right here, highest value of that would be 1. And then, of course, if we're on the horizontal diameter, what's the value of this vertical distance on the horizontal diameter? And the bug hits there twice, right? At an angle of 0 radians, and then also at, when else does it hit 0? Pi radians. That's here. Remember, halfway around the circle is pi radians. And then also hits back at 0 at 2 pi radians. Where does it hit negative 1? At what angle? 1.5 pi. Pi and a half pi. At the bottom of the circle is 1.5 pi swept out, and the vertical distance is a fraction of a radius length, negative 1, a whole radius length below. A whole radius length below. Okay, so these values would be true whether it's a bug going around a fan or the second hand of your watch. Does anyone have watches like that anymore? So if it's a second hand of your watch going around, or if it was some planet orbiting a star, okay, it was a circular orbit. These values would be the same. So this relationship right here is universal, and that makes it very special. And so that function, when you input the measure of the angle in radians, swept counterclockwise from 3 o'clock, and you output the vertical distance above the horizontal diameter in fraction of a radius length, there's a special name for that. Some of you know. What is it? So input is the angle, output vertical distance. This is called the sine. But maybe you've never thought of it this way before. Okay? That input-output relationship is the function, the sine function. Input is the angle, measure of the angle swept counterclockwise from 3 o'clock. Output of that sine function is vertical distance above the horizontal diameter in fraction of a radius length. Fraction of a radius length. So now what if I wanted, for the fan example, I want to change this function so it outputs it in feet. So what is the highest in feet that it gets? 2.6. This is still 0 feet. And then the lowest that it gets? Now I want to use this function to write a second function that outputs the height of the bug above the horizontal diameter in feet. So say right here, when we're at half of the fraction of half of a radius length here, what's the height in feet? 1.3. And what's the value of sine? Half of a radius length. So when we're at half of a radius length up, we know that we're 1.3 feet up. When we're a whole radius length up, we know we're at 2.6 feet up. So how can I write this function g theta? John?
2.6 multiplied by sine of theta.
He wants 2.6 times sine of theta. Because if we think of that sine theta as the fraction of a radius length, then we just always want to take the fraction of what? 2.6 feet. We just want that fraction of 2.6 feet. How do we get that fraction of 2.6 feet? We just multiply. We're going to take this fraction of 2.6 will give us now in feet rather than in fractions of radius length. So this gives the gives it in feet. So what if the radius of my second hand on my watch is 7 millimeters? And I want to measure the vertical distance above the horizontal diameter on my watch in millimeters. What will the function be? 7 times sine, because that sine will give us that universal fraction of a radius length that we are above or below. And so we're going to take, we want that fraction of whatever our radius is. In that case, 7 millimeters. Okay, so it got quiet. Is that because you're listening really hard or it's not making sense? Does this make sense? So the key is that you think of, so we know that sine is, it outputs a vertical distance above the horizontal diameter, and it's in the unit of the fraction of the radius length that we are above or below if it's negative. And therefore now given any radius, we want to take that fraction of the radius, so we're just going to multiply by 2.6, or by sine. Any questions? Okay, so now we want to go to, look at horizontal distance right of the vertical diameter. This is a little trickier because, so horizontal, right, we said to pinpoint the location of the bug, we need 2 output quantities. First we need the vertical distance, which we just did analyze. Now we need horizontal distance. To the what? What was our positive horizontal distance? Right of vertical diameter. Okay, we're still going to do that in fraction of a radius length. Here's the tricky thing about this. We're measuring this horizontal distance. Before, when we measure the vertical distance, it just matched right up with our vertical axis, right? The vertical distance of the bug was our y-coordinate on this. But now we're measuring horizontal distance, and then we're taking that value and we're putting on a vertical axis when we make this graph. Okay? So for instance, right here, when the angle measure is 0, what is our value of output? What is our horizontal distance right of the vertical diameter? 1 full radius, right? So how does that graph as a point? Where are we going to start? Up at 1 now. Why? Because this vertical axis for this graph over here is measuring horizontal distance from the vertical diameter of the bug in the circle. So in that first quadrant, so we're going to do it. So in the first quadrant, does the output, does the horizontal distance increase or decrease? Decreases from what to what? 1 to 0. See, it starts at 1 whole unit, and then when it gets to the top of the circle, now it's at 0 radius lengths, or fraction of a radius, to the right. Okay? And so, again, I'm showing you those changes. So the horizontal distance decreases. Are the changes increasing or decreasing? Talk to the person next to you. Are the changes increasing or decreasing? Watch them up top. I'm showing you up top. There's the first change. There's the next change. There's the next change. There's the last change. Do they increase or decrease the changes in horizontal distance? Okay, Chad back there, what do you think? So the horizontal distance, is the horizontal distance increasing or decreasing? Decreasing from what to what? From what value to what value? If we're measuring in fraction of a radius length. So what's our initial value of output? What's our initial value of horizontal distance here at theta equals 0? How many radius lengths are we to the right? 1. So the output, increasing or decreasing? From what to what? 1 to 0. Here we're at 1 radius length to the right. Here we're at 0 radius lengths to the right. Okay, now the changes. Are the changes in horizontal distance increasing or decreasing? Are they negative or positive changes? Negative changes. We're decreasing in output, so they're negative changes. More or less negative? More negative. Therefore, these changes are decreasing changes. It's the same thing again. These are decreasing changes. So the rate of change is? And the graph is? Concave down. Let's see it. Ready? Here it goes. Decreasing changes means a negative rate of change means concave down. I'm going to post web work this morning.